Thank you very much. So I will try to speak loud so you can hear me in the back. Can you hear me now? Could you just wave a bit? Okay, good. Thanks. So I will talk about follow on where Jim left off, basically, and talk about a particular problem in string theory where machine learning has been applied in recent years, and that's to learn Calabi-Yau metrics. So this is the problem is to learn the Ritchie-flat metric on a Calabi-Yau. And this is based on work done in collaboration with Andre Lucas and Fabian Rulli, who are here, and Robin Schneider, who was a PhD student in Uppsala, and Jakob Hendy and Moritz Wange, who are present PhD students in Uppsala. And there are 2 papers related to this and some work in progress. And during my talk, I will also touch upon work that has been done by many other groups. So we are not the only one working on this. It's a big, interesting topic to work on. And I hope also in the discussion or in the questions afterwards that if there are some things that are left out, that maybe some of the experts in the room can fill that in. So there's an alternative title for my talk, which is that with very simple machine learning techniques, we can learn Calabi-Yau metrics. So the slogan that I'd like you to take home for this is that we don't need to go very advanced in machine learning to actually resolve some of the issues we've had in theoretical physics, and that's rather surprising. Maybe that is hinting at something in the Calabi-Yau geometries that we haven't appreciated so far. So it's a good message to take home. Why is this? Why does these simple methods work so well, and can we learn something from it? So let me set up the problem and motivate why we want to do this. So we're from the context of complexifications of string theory and the swampland, the Calabi-Yau geometries have a special place. So they are very popular in these constructions, and the reason for that is that we know a lot about Calabi-Yau manifolds. In particular, we know a lot about the topological properties from algebraic geometry, and we can construct examples. So they are very non-trivial geometries where we can still construct concrete examples and we can compute things in detail. The topology and the geometry of the compact dimensions in the string complexifications is always key to the physics that we observe. And we've heard something about that when we talked about in the conference so far. So in the swampland setting, for example, the swampland distance conjecture, which we've heard about how we can test it in the Calabi-Yau moduli space, is something that is we can explore using once we know more things about the geometries that we are looking at. So the Ritchie-flat Calabi-Yau metric then that is the topic of this talk has the information about it has a lot of information about this compact geometry and where it's how we can measure distances on the geometry, what kind of curvature it has, and what masses and so on we get for fields in string complexifications. So the question that we want to ask then in this talk is, can we compute it in examples? And it's important, since yesterday we talked a lot about very general results in the swampland setting, to remember here that we are working on examples. So we're doing very specific computations on specific geometries. And this is so that we can use these machine learning techniques and do numerical computations. So in order to do something like that, then we need to construct our examples. And there are huge databases of Calabi-Yau geometries available that we can use. And the thing that we are drawing on in these machine learning implementations are constructions of Calabi-Yau geometries as some sort of hypersurface or intersection of hypersurfaces in a simpler ambient space. So given this simpler ambient space, we can compute certain things, and this allows us to make progress on the Calabi-Yau metric problem. So a particular geometry that is very important is the quintic. So the quintic is given by a quintic polynomial in an ambient space, which is the complex projective four-dimensional space, P4. And this is one of the geometries that is collected in the CC database. And so this is a simple and kind of simple geometry that is kind of like it's the favorite example where most of these numerical methods have been tested. What has happened in recent years is that we now we have evolved these numerical methods and we can apply them to more advanced settings, so to any kind of generalization of the quintic in the CC space, so where we replace the ambient space P4 by a Cartesian product of predictive spaces. And we're looking at various polynomial equations in this ambient space that give us a complete intersection Calabi-Yau. Or we can exchange the ambient space and look at these toric ambient spaces instead. And that, in particular, can be done if we're looking at the Calabi-Yau manifolds that we get from the Kreutzberg database of toric varieties. So the problem we want to solve is that we want to find the unique Ritchie-flat metric on the Calabi-Yau, and we know that this exists from the Calabi-Yau theorem, which is stated here. So if X is an n-dimensional compact complex Kähler manifold with vanishing first Chern class, then we know that in any given Kähler class, X will admit one unique Ritchie-flat metric, which is the one that we're looking for. The problem is, of course, that in proving this, this metric was not constructed. So we don't have an analytic expression for the Calabi-Yau metric, as Jim was mentioning in his talk just before the break. And also, if we would want to just try to solve for this and say that, okay, I want to find this metric, I want to solve the condition that the Ritchie tensor should be 0, then this is a highly non-trivial, non-linear PDE. So it's a very hard mathematical problem to solve. Of course, since we are in the Calabi-Yau space, we know a lot more, and this is, goes back all the way back to the work of Yau. So one thing we can say is that if we want to stay in the same Kähler class, then and find the Kähler metric there, then that corresponds to looking for a Kähler form in that Kähler class. So something that is related to some reference Kähler form by adding an exact piece. And we can write that exact piece as del bar of a function phi. Then the second realization of Yau is that we can rewrite the condition of being Ritchie-flat as this Monge-Ampere equation here, which is saying that once we have found this Kähler form that we're looking for, that gives us the Ritchie-flat metric, then if we wedge that 3 times, then that will give us a volume form. And there is also another way of constructing a volume form in a Calabi-Yau, which is by using the holomorphic top form of the Calabi-Yau. So this is called omega here. It will be a 3,0 form on a 3-dimensional Calabi-Yau. And if we wedge that with its complex conjugate, then this will also give a volume form. Now, since these two are volume forms on the Calabi-Yau, they need to be related by a constant, or they need to be related in this way. They need to be proportional. And this kappa here has to be a constant, basically because of uniqueness here. So what we see here is that from this reformulation as a Monge-Ampere equation, we can translate this condition of Ritchie flatness into a second-order partial differential equation for this function phi here. So this is an immense simplification of the problem and something that is essential to the implementations that we will talk about. So very importantly here, once we have constructed our Calabi-Yau example, we can compute such a reference Kähler form, and we can also compute this holomorphic top form. And this is known how to do this from the way that we construct these geometries. And I will not go into the details in the short time that I have today. But importantly, we can compute them. So we can then set up the problem, our numerical problem, say that we want to solve this Monge-Ampere equation, yeah? And we want to do this numerically. So what do we need to do then? Well, we need to sample points, random points on the Calabi-Yau, where we can compute these reference forms, the reference Kähler form and the holomorphic top form. So we compute those, and then we solve the Monge-Ampere numerically using some numerical method to do that for the Kähler form that we're looking for, or for the function phi, which is related then to the Kähler potential. And then we check that the solution is good. So we check that the Monge-Ampere equation holds and that the Ritchie tensor is 0. So this is the strategy that is employed then in any kind of numerical method. So this is a long-standing problem. It's been around since Calabi-Yau manifolds were invented. And there have been different numerical approaches to solve this problem. And this is a list, a non-complete list of references. So Jim mentioned the canonical method, which is called the Donaldson algorithm, which is the first, which is a nice and very mathematically well-controlled way of solving this, but that is computationally slow. And then there are other approaches that have been employed to this, and what we're focusing on today are these machine learning approaches. So one important thing to say in this, related to these more recent developments, is that if you're interested in this and if you want to apply these machine learning methods to your own setting where you have some problem where you want to compute the Calabi-Yau metric, then there are packages that are available. And these packages are open source. They can be manipulated to do what you want to do. And all of these, so they are available and you can use them. And it's also highly encouraged to contact the authors of these packages and have discussions about what kind of modifications can be made. Because it may be that you're interested in some particular situation where you don't really need the Calabi-Yau metric, but you need some modification of it. And then starting from these packages might give you a lot of leverage in reaching that goal. So that's a bit of publicity. I've been working on this middle package here, CY metric, which is the one that I will talk about in this talk. But the other ones are equally interesting packages, and they differ in some details that I might touch upon, but if you're interested in that, you can also ask me in the break. Okay, so since this is a long-standing quest, let me say something about the different approaches you can take. So there's basically two different approaches that I like to highlight. So one is where you do something that is that was pioneered by Donaldson in his algorithm, which is that you focus on the Kähler potential of the metric that you want to learn, so the Ritchie-Flat metric, and you look for solutions. So you look for such Kähler potentials that fall into a particular class, which are expanded in a particular basis of homogeneous polynomials. So the important thing is here is that you can choose a degree of these polynomials, and that will give you a finite basis. And then you expand your Kähler potential in that basis, and then you can apply different numerical techniques. So in the Donaldson algorithm, it's a fixed point iteration scheme. And you can also write down a functional and minimize an NAD functional and minimize that. Or you can employ machine learning to look for these parameters here in this matrix H. However, as we heard in the last talk, machine learning and neural networks give you a different way of approaching this problem, using that neural networks are universal approximators. So you can alternatively, instead of writing down this particular ansatz for your Kähler potential, you can search for this freely using a neural net. And what you do then is that you set up your neural network, much in the way that Jim talked about in this last talk, and then you train it in order to minimize some loss that is related to the conditions that you want to satisfy. And this is what I want to detail now. So the machine learning implementation in that case is then that you have your point sample, and this will depend on the moduli of your Calabi-Yau. So the moduli and the points are sort of your input to the machine learning model. This machine learning model is some sort of neural network, has some particular architecture, some nodes that are connected. And this will be optimized using a training algorithm so that the loss function is minimized. So this is an optimization problem. Then this will give you a prediction for the metric, and you will have to check that this metric makes sense. And there are error measures that are used for doing that check. So I will talk about this particular implementation, which is the CY metric package. And here are some brief summary of what this is. So this is a package. It's written in Python and Mathematica. So it has two interfaces depending on your what you like. And it decomposes into two pieces. One is a piece which generates the points in your sample. So we need to sample points on the Calabi-Yau. This is a non-trivial problem. And this is something that you always need to do in these implementations. And then there are these neural networks that give you the Calabi-Yau metric. So let's talk about the point generators. So the first thing we need to do then, in order to have the points, is to think about what we will use them for. So one thing is that we will use them as input to the neural network, but we also want to use them in the end when we check the performance of our approximation. So we want to compute some error measures. And these error measures are defined here. It's called the sigma measure, which, as you can see, is a measure of how well we are fulfilling our prediction, J prediction here, is fulfilling the Monge-Ampere equation. And then there's the Ritchie measure, which is checking. It gives us one measure of how far we are from being Ritchie flat. And these measures here are integrated over the manifold, so we want to see how we're doing globally on the manifold for these measures once we're done with the training. So in any numerical implementation, if we're computing integrals, we need to do that we need to trade the integral for some sort of summation. So we do this with Monte Carlo integration. This is also standard. These kind of error measures and the way of computing these integrals is the same way that we do for different numerical methods. So has nothing to do with machine learning. But when we generate points, we want to be able to compute such integrals, which means that we need to sample points with respect to a known measure. So a point generator should give us a sample of points that are randomly distributed over the Calabi-Yau, and this distribution is with respect to a particular measure, so a particular metric on the Calabi-Yau. Now, we don't know the Calabi-Yau metric, so when we start, so we take this reference metric, which I will refer to as the Fubini-Studi metric, because that's what it is, and this will be the measure that we sample with respect to. So there are methods to do this. There is a well-known method for which was developed for the quintic, where you use certain properties that are given by this mathematical theorem by Schiffman and Saldich that tells you that if you sample points in a particular way on the ambient space of the Calabi-Yau, so here the P4, then these points that you sample on the P4 will be distributed with respect to the Fubini-Studi metric on the P4. And if you sample two such points and connect them with a line, then this line will intersect your hypersurface in a number of points. So here we have a quintic hypersurface that will be 5 points. So you do this many times, and then you get many points on your Calabi-Yau, and they will be distributed with respect to the Fubini-Studi measure on your Calabi-Yau. So if you restrict your Fubini-Studi measure on the ambient space to the Calabi-Yau. So this is all very good. So you have your sample of points, and this can be generalized. So it can be generalized to all manifolds in the CC database, and we generalized it to all Calabi-Yau hypersurfaces in the Kreutzer-Skarke database. How am I doing with time? Okay, then I will skip the details of this implementations, and I will tell you something about the machine learning bit. So basically, the point sampling is solved, and it relies on in particular on the Schiffman-Saldich theorem. So the machine learning implementation in CY metric is one of these free implementations. So we're not expanding the metric in some particular, or the Kähler potential in some particular basis. Rather, what we do is the following. We input the moduli and the points into a neural network. This neural network consists of a number of fully connected layers with some nodes. We go from one layer to the other by this affine transformation that we recognize from Jim's talk, and then we have a nonlinear addition to that here. And then in the end, we output either the metric or the Kähler potential that we're looking for. So there are a number of choices here when you set this up. So you can choose how many nodes you have in different layers, how many layers you have, what kind of nonlinear functions you have, and so on. You can also choose what you want to encode here. So if I want to predict the Kähler potential, then I have already I have already included that this is a Kähler metric that I will get out of this Kähler potential. Whereas if I predict the metric freely, then I'm not guaranteed that this is Kähler. So if depending on those architectural choices regarding to the network, I will need to include loss functions that will encode the other constraints. So in CY metric, there are a number of different, more or less free ways of doing this. So ansatz, say, for the metric, that looks something like this. So either you use the network to predict the full metric or some addition to this reference metric that we have, the Fubini-Studio metric, or you can go to encode that this should be Kähler, and then you have the most constrained architecture here for the network. Okay, so then you have your network, you have your parameters, they are initialized, and you want to train it. So in order to tell the network where it should go, you need to tell it what kind of constraints it should fulfill. So here, because we don't know what the Ritchie-Flat metric is, we cannot use supervised learning. We have to use semi-supervised learning when we are defining these custom loss functions that encode our mathematical constraints. So for example, for the Monge-Ampère equation, we write down a function which is checking how well we are, so how the volume form that we get from the metric is comparing to the volume form that we get from omega wedge omega bar. And then we can compute this with, so we're doing this over a number of points, and we're taking some of the norms of these. And we can do this with some different, giving different weights to different points, which is also a bit of choices related to that. Then if we have one of these freer metric ansatz, we also need to have further losses. So we need to have something that encodes that the Ritchie tensor should be 0, that the metric should be Kähler, that the metric should be transformed in the right way as we go from one patch to the other. We're doing this on a manifold. We need to check that the metric that we get is global. And also something if we're training on more complicated or more advanced Calabi-Yaus that have more than one Kähler parameter, then we need to check that we stay in the same Kähler class, and that needs a Kähler class loss. So we set this up, we have these loss functions, and then we can do the training. And after we train, we then check with these benchmarks. So then we check that we're doing the right thing. And if we are working on a Calabi-Yau with more than one Kähler parameter, then we also need to check again that we stay in the same Kähler class. And this requires checking, for example, that the volume stays constant and that certain topological quantities that are related to the Kähler class also stay constant. So let me show you some experiments in the last minute that I have, and then we can open up for questions. So one thing that has been a bit of an issue for example, the Donaldson algorithm, is that you can do very well on, since you're relying on this expansion in a polynomial basis, you can do very well if you have a lot of symmetry in the problem, so that you can reduce the number of elements you have in this, the number of parameters that you need to learn in this emission matrix HAB that I showed you some slides ago. However, with machine learning techniques, these free machine learning techniques, this is not really an issue. So we can train for the quintic on something that is highly symmetric, like the Fermat. It has a lot of discrete symmetries. And we can train on something that is just completely generic when it comes to complex structure moduli. And we see that, sure, it's faster to train on the Fermat. We reach lower levels of these loss functions during training and of the error measures that we check afterwards. So they are here. It's a bit tricky to see the scale here, so I'm sorry for that. But basically, training results in better approximations on the Fermat. But training also works on this non-symmetric Calabi-Yau. So the methods work. And we can look at more complicated example. This is a particular Kreutzer-Skarke example. Training works here as well. The losses go down, the volumes stay constant, the sigma measure goes down, the Ritchie measure does something funny at the beginning, but then it goes down. So training works also for more complicated Calabi-Yaus. So I will skip the further developments and go to the conclusions. So the main message is that with these simple neural networks, we can learn Calabi-Yau metrics. We can do so for a wide variety of Calabi-Yau manifolds. The name of the game in this free implementation, this kind of architecture that we have developed, is to encode the mathematical constraints in loss functions. Now, this is a choice one can make. How much do we want to encode in the architecture of the neural network, and how much do we want to encode in the loss functions? And there are pros and cons with these different choices, and there are different developments in the literature where this has been discussed. So there are places that one would want to go in the future. So one thing is that with the CY metric package in particular, we can compute the Calabi-Yau at a given point in moduli space, but it's just computed at that point. So if we want a moduli-dependent Calabi-Yau, then we would need to do something more. And there are some developments in the literature. Fabian and Sven and others have worked on this. And in particular for simpler Calabi-Yaus like the quintic. So there's there's also this discussion about what kind of architecture should you have that makes it easier or less easy to learn the modular dependence. Then, of course, applications in physics is very interesting. And also going beyond the Calabi-Yau case to look at other kinds of geometries is something that one could surely imagine to do in this setting. Okay, and I'll stop there. Thank you.
Thank you very much, Magdalena. Questions, Thomas?
Yeah, thank you. Thanks. It's about the applications in physics. So Yukawa couplings are an example of physical data for which you actually need to go beyond, well, you need to know the metric a bit to compute. But say other physical data is often, I mean, an example is, say, if you do conformal Calabi-Yaus, then the Monge-Appert equation will be, there's another one, which is related to the warp factor equation. And I think, I mean, that seems an important one because there's lots of discussions about how you glue a throat into a compact Calabi-Yau and what happens at the gluing. Do you think this is feasible, or is that a little bit beyond? Because that's a double, I mean, then you have two equations.
I think it's certainly something that one should attempt. I have not looked at the details, so I don't know if it's feasible, but I definitely think one should attempt it. So Andre made a very good comment yesterday in the discussion that if you're looking for something that is only going to affect a very small portion of the Calabi-Yau, it might be hard to detect it with these numerical methods. So maybe you need to sample points, over-sample points in that particular region in order to see this. So, but
how do you measure small?
Yeah,
because you see, for warp throat, it can actually dominate the volume.
Yeah, so I think it's definitely a very interesting problem to look at. Yeah. And if there is, I mean, given, like in this case we had the Monge-Ampere equation. So given such equations, one can certainly, set up an architecture that goes and looks for solutions for those equations using stochastic gradient descent, which is what we're using. Yeah. So we're training the network with some optimization routine, and then one can attempt to look for solutions for different equations. And what this corresponds to is that you need to change your loss functions that you have. So these loss functions that you have here would then need to be updated with the equations that you want to solve. That's basically what you want to do.
Yeah. A quick follow-up to Thomas' questions. When you include the warp factor, you also have to include the branes. And how do you take into account the...
I don't. So short answer, I don't know. And it's maybe one should excise them in some way. But I'm just speculating here. I haven't really thought.
As a comment, it depends a little bit what you want to do. If you want to, for example, reduce metric from the brain, you could get that.
Yeah.
If you know where the brain locus is, that's perfectly possible because unlike discrete methods, the neural network will give you the metric everywhere, including where the brain sits.
Yeah. That's a very important point. So I didn't really talk about that here, but we are training the network in certain points, and then we are testing it in other points. So we are checking that the metric that we learn is not only true in the points that we have sampled on, but it also interpolates, or it works in other points. So it does give us some global information.
Okay. No. Okay. Yeah. So.
Thanks. So regarding some of the physical applications, my question was like, how easy would it be like to compute the moduli dependence of the first KK modes? Because usually we have like some results regarding like the very excited states, but in some sometimes what might be interesting for us is like the first ones, which are like the ones that might not be like as homogeneous spaces, or like you don't have bias asymptotic formula or some mathematical results that tell you how they go. So how easy would it be like to get model dependence of the first excited KK modes?
Yes. So the person to talk about this is I think maybe Fabian. So that I just wanted to talk about these works in relation to your question. So looking at the massive modes on Calabi-Yau manifolds using numerical metrics is something that has been done. And so these papers by Anthony Ashmore and Ashmore Rula and Ahmed Rula and Fabian and collaborators, they are looking at exactly that on the quintic and using the moduli dependent metric also in one of this. So this is something that you can do, and you can see very interesting behavior of these massive modes and how they change as you move in the moduli space. So this is something that you can do, and I would just direct you to these papers. So these are papers from Ashmore and Rula and Ahmed.
Okay, thanks.
And maybe Fabian, if you want to comment.
Thanks.
We're running behind.
Yeah,
so
sorry.
Thanks for that very nice talk. I had two questions. One question: for your point sampling, as you start from the Fubini-Studi metric and approach the Richterstadt metric, do you adapt?
So the points are sampled with a known measure. Mm-hmm. And then when we are computing, so when we're using those points for computations in various places, and particularly when we're computing these error measures, then we are correcting for that by computing, for example, integrals as these weighted sums. So these weights here, so we know the Calabi-Yau measure because we can. That's given by the omega wedge omega bar. So this is something we know. I can compute, and then we sample with respect to this measure. So this is something we can compute then from the reference Kähler form. So this is something we compute then in every point. So we have this information, and whenever we were computing something, we're using that way.
So assuming you have enough points to begin with, then it's going to work.
Yeah.
Thanks. Second question: can you, as an application, can you start finding minimal surfaces in a given homology class if it's not calibrated, for instance?
I think that's a very interesting problem to look at, and I would say yes, but no one has done it. So I think it's but really using the metric to compute the volume of a cycle is something that you can do, and then you can look for how you could adapt the metric so that the volume becomes minimized. So it's not a problem. I don't think anyone has really worked on that. Now I'm looking at other people.
It's very natural. How to cycle the submanifolds.
Yeah. So it's the sampling of sampling of submanifolds is something you need to think about first. Once you have that, then.
Yeah, I guess
Thanks.
in my cases where you don't have a calibrated representative.
Yeah, exactly. I guess you could test it first with calibrated ones, but yeah.
Very important non-supersymmetric limits.
Okay, I don't see any further questions, so let's thank Magdalena again.